The next application I'm going to show you is testing if a graph is connected or not. So we're going to check if a graph is connected or not. So we're going to see if a graph is connected or not, or we're going to test its connectivity. Now, I want to remind you of a couple of quick terminology things. So what does it mean for a graph to be connected? So a graph is connected. So for graph G, it is connected if the following is true. For every pair of vertices, so any one of those vertices in that graph, there has to exist a path between them. There exists at least one path from U to V. So if this is satisfied, so let me show you an example of a connected graph. So I'm just going to have a bunch of vertices here, and I'll just add a triangle at the bottom. Look at that pretty little triangle. So if you take a look at this graph, notice that there is an edge. So if I pick any two vertices in this graph, there exists a pathway, a sequence of adjacent vertices that can get me from one vertex to any other vertex in this graph. So this graph is connected. However, I can make it disconnected, meaning it's not connected, by simply doing the following. I can introduce two more vertices, connect them like this, or maybe I can introduce what we call an isolated vertex. Notice that now it does not exist a path from, say, this vertex to that one. They're separate. So in terms of connected components, which we're going to talk about at some point, we have 1, 2, 3 connected components. And this graph, by definition, is disconnected. So let me just fix that E there. Just staring at it. It's like, nah, let's fix that. So we would like a very simple test to know if a graph is connected or not. So here's a neat observation. Do you recall when we've seen depth first search or even breadth first search? Do you notice that when we start at some vertex in the graph, do you notice that we'll label all the edges of vertices that are reachable from the start vertex? So we'll get to all of them. So notice that it will mark this one, 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 and all these, but it will not mark those other vertices. That's on a single call of DFS given a start vertex. So these are all reached, all these vertices and edges are reachable from this vertex. So we actually can use this information as a test to know if a graph is connected or not. So if I fail to mark all the vertices in the graph, we know that it's disconnected. And that's exactly all we have to do to test if a graph is connected or not. So here's just an example of how I can do this. So here we go. So I'm going to call this algorithm connected. So I'll call it connected, and it's given a graph. So it's not given a start vertex or anything like that. It's given a graph. So what I'm going to do is I'm going to adapt the graph traversal of the entire graph, meaning that I'm going to just start this up at some vertex. I'm going to allow it to do a depth first search or a breadth first search. Doesn't matter which one. And we're just after that just going to scan through all the vertices and see if all of them are marked. If they're all marked, then you're good. It is connected. Otherwise, it's not. So as input, we're given graph G. G is equal to VE. So we got our vertices and our edges. And I assume that these vertices and edges can be marked and labeled. And as output, all it's going to do is tell us true if if G is connected. if G is connected, and it's false otherwise. So here's what we're going to do. Now, you can have the same setup we had before that makes sure that the graph is entirely clean, meaning that all the vertices are not marked, all the vertices are not labeled at the beginning of this process. We can introduce that at the beginning of this algorithm if you would like. For the purposes of the time, I'm just going to skip past this. Assume that the graph is what we call, it's clean. There's nothing written all over the graph, okay? I don't have the X's or labels or anything on the edges, but you can add that at the beginning of this. So we're going to just start off by, you just consider any vertex V. So any one. You could be the very first one that you could pull off. It can be anyone. It can be an arbitrary one. You could flip a coin. It doesn't matter. It could be any one of the ones in this graph, or any undirected graph like this. So then you're just going to run DFS. Keep in mind, if you don't like DFS, you could just put BFS here. Doesn't make any difference. And then all I do is I just go through each one of the vertices and I just check if it's marked or not. For each vertex, V and V, we're just going to do the following. So all we're just going to do is we're going to check if V is not marked. So if V is not marked, then all you're going to do at this stage is just return false. Because so you might say, Dan, why? So suppose that I gave you this graph, for example. If I did DFS on, say, this vertex, say U is V, it will mark all of these. And then I scan through each one of them and I check, is this one marked? 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 Oh, that one isn't marked. It means it wasn't reachable, meaning that there does not exist a pathway from V, or U in that picture, to that vertex. So that means it's disconnected. So then you just go through this loop. Gonna add the curly braces. Never forget your curly braces. It's always a good time. Then, once you've examined all the vertices, if all of them are marked, meaning that this will never occur, you're going to return true, meaning that the graph is connected. Piece of cake, right?